Howdy and welcome back. We're going to introduce in this video function pointers, and I'm going to try to do it in a way that will strike some familiarity with something you've already seen before. Hopefully this video is straight forward. Hopefully I don't get off on too many tangents rambling, but I do hope that by the end of it, function pointers, um, the concept, how they can be used, will hopefully become clear. And to do this, I want to start out with kind of just thinking about functions in general. We're going to make a mistake, we're going to make an observation, we're going to relate it back to a compound type we've talked about, and then we're going to move forward, and hopefully this will slowly come together. And again, the syntax that we're going to use here to declare pointers or function pointers is going to be a little, it's not pretty. But let's go ahead and just look at this. So functions, we can invoke a function using the call operator, which is going to initiate the function call process. So imagine that we're in a main and we invoke my silly function with the integer arguments 1 and 2. Well, before we get into how this call is going to be processed, let's first look at our definition of my silly function. It has 2 integer parameters. The return type is a Boolean, so that I could get this into a standard output to standard output. And let's just go ahead and look at the body. It's doing nothing interesting. It's printing to std out, entering my function, parameter a, initialized with, well, whatever values stored in a at this point, parameter b initialized with whatever stored in b. Okay, do something interesting, but it's not going to. That's why it's silly. And then exiting our function. So if we go ahead and invoke or execute, maybe say some sort of application that makes a single call to this function within its main, here's kind of what's happening. So if we look, we're back to our old friend, the memory diagram. So we're in main and we're executing through line by line. Something comes before this statement, statement, maybe, maybe not, whatever. So we're going through main and then we hit this function call, my silly function. What's going to happen is the execution of main is going to be paused. An activation record for my silly function is going to be pushed to the stack as shown below. So enough memory to hold the parameters a and b will be reserved in the activation record for my silly function, along with some additional housekeeping information that we haven't really talked about. Okay, so that memory's been allocated. We now go ahead and initialize the parameters with their arguments. So a will get the integer value of 1, b the integer value of 2, and then we'll begin executing the code. What this requires is that we have to move out to wherever this code resides in memory, right? So if you remember our address space, we had that code static region, which is where my silly function's definition would reside. We have the stack, which we're drawing below. And because we're not dealing with dynamic memory, I didn't draw it in our memory diagram, but there's also some region of memory reserved for the free store. So at this point, and I guess not reserved because the stack and free store grow to one another, but there's a region called the free store. Cool. Okay. So as we're running through this code here, that means that somehow we're going to have to get up to the base address, if you will, of where this function is in memory, right? Kind of where it starts, and then we'll begin executing the code associated with it. So let's just assume that maybe kind of one line corresponds to maybe, I don't know, something up there in memory. So let's just look at this like line by line. So we've moved to where my silly function begins in memory. We hit the first statement, and the code there is going to write out to standard output, entering my function. We're now at the next statement here, which outputs that parameter a initialized with, the next statement, parameter b initialized with, next statement, do something interesting, next statement, exiting my function, and then we hit the return statement. When we hit the return statement, remember that the activation record for this particular invocation of my silly function is removed from the stack. And where do we end up? Well, we're going to somehow find our way back to, in this case, assuming it's a main, where we left off. So we just executed that statement, and upon returning, we'll pick up right there at the statement that comes directly after this. So notice here that as we're executing kind of the instructions for our program, we're in some region of memory and we're kind of going through that, which means that theoretically, if you knew where, say, this definition was in memory, you could go out and begin executing that function, right? Similar to how with kind of arrays, right? So if you think about arrays, what did the array's name? So if we had something like int r as an array, and I don't know, let's initialize it with 1, 2, 3. What happened when we std out array? Well, we received the base address of the array, right? And then we could kind of offset into that array to access its various elements. What we're going to see here is that you can kind of think about my silly function if we just were to write the name as doing something similar. And I'll go ahead and show you what I mean by this. And I'm going to do this by saying, okay, however, we all make mistakes sometimes though. So we went through that beautiful example on the previous slide, and then we just modified kind of our standard output statement. And again, this could happen anywhere within our application. It's probably easiest to think about this as the sole thing that our main function's doing, whatnot. But notice here, I've output just my silly function without the call operator. So just the name. And then I went ahead, compiled, executed this, and guess what I observed in standard output? An address. And guess what that address is? It's going to be similar to the address that would have been printed if we wrote something like int r 1, 2, 3, standard out r. In this case, the name is resolving to the base address of our array. So that's going to be here, the base address. Likewise, you can think about the function name as resolving to where that function's code begins in the code region of our program's address space. And if just look at how this is kind of relating back to the array. You output just std cout an array's name. You see the base address. Assume something similar is happening for our functions. You just provide the function name without the call operator, so without the parentheses. Assume that you're going to get the address to where that function's code begins in memory. And there's a slight disclaimer here at the bottom where I write, the default behavior in your environment will more likely than not output the integer value of 1 when the function name is passed to standard library cout. I'm not going to get into why this is, but you can force the address to be printed by inserting reinterpret cast to a void pointer with my silly function, so the name of the function in the output stream. And in that case, you would see the address. But again, for our discussion today, assume that anytime you're just dealing with the name of the function without the call operators, you're getting back the kind of base address as to where our definition for that function begins in memory. And that will make everything moving forward a lot clearer. So again, let's assume that a function's name will evaluate to its base address. And this makes what's to come easier to understand. So my silly function, you see that without the call operator, boom, assume you're getting an address back. Given a function's name evaluates to its base address in memory, so we're dealing with an address as we have with an array's address, an address to some sort of object. The question becomes, well, can we use its address to initialize a pointer? And the answer to that question is going to be yes. And well, it doesn't look too pretty. So here's how you can create a pointer to a function. How this is going to look is as follows. The first thing we're going to see is the function return type. So if we were creating a function pointer to our my silly function, notice that its return type is bool. So in this case, we would have bool as the return type if we were creating a function pointer to my silly function. Next is going to be the name of our actual pointer. So in this case, if we want to name it my silly function pointer, that's totally cool. And that would be what is associated with this. It's the pointer object's name. So in this case, we're creating a pointer named my silly function pointer, and it's going to be a pointer to a function that returns bool. Next is going to be the function's parameter list. Oops, I keep getting to my eraser. So function parameter list types, because if we're having a pointer to a function, we have to tell the compiler not only what this function would return if we use our pointer to invoke the function, but also what the parameter list is. So in that case, if we come up here, we can see the parameter list was 2 integer objects. So we'll go ahead and specify that here. So again, notice the use of parentheses, and we don't need to provide any sort of identifiers for the parameters. We're just specifying the types out here. And now finally, the last thing we're going to do is, let me find another color, provide the address, which we like to use to initialize this pointer. This would just be that function's name, my silly function. And at this point, my silly function pointer is going to point to my silly function. And that means that we can actually invoke my silly function through the my silly function pointer. And what that would look like would be this, my silly function pointer. Let's say we want to provide the arguments 1 and 2. That would cause my silly function to be invoked with the arguments 1 being used to initialize the parameter A, 2 being used to initialize the parameter B. And if you look at this, it's pretty much equivalent to calling my silly function with the same arguments. Cool. So let's go ahead and look at this in action. So maybe you can read this a bit better than my handwriting, but we have the same setup here. We're just going to do exactly what I mentioned on the previous slide. So we're going to introduce my function pointer. So different name, but my function pointer is going to be a pointer to a function that returns a Boolean value who has 2 parameters of type integer. And we're going to initialize this pointer with my silly function. And then at that point, if we were to invoke the call operator, or I guess go ahead and interact with my function pointer with the call operator specifying 2 arguments, we're going to actually invoke my silly function with 2 arguments. And as we can see here, the output of invoking my silly function in this manner is identical to how it would have been if we had invoked the function with my silly function through its name with the same arguments. Now, if you think back to when I was introducing, I believe, references and pointers earlier in the course, I kept saying the semantics of argument passing are identical to that of initialization. So I said, if you see a reference kind of out there in main somewhere, the behavior you're going to observe in that it's another name for some sort of object is the same that behavior that you would observe had you seen a reference in a parameter list of a function. And function pointers are no different. So revisiting our filter movies object, if we wanted to pass a function to filter movies as through a function pointer, we could go ahead and do that. In this case, and I'm deviating from the standard template library function type because that's going to be a catch-all for kind of multiple different function-like things that can be passed to a particular function. But if we were just dealing with kind of functions in general, so not function objects, not whatever, just what we've talked about today, we could go ahead and create a parameter named filter, who is going to be a pointer to a function that returns a Boolean value, who has a single parameter, which is a reference to const of a movie object. So now note this. I mean, that's the only thing we've changed was the parameter. And if you notice here, how we could invoke that function is no different than what we saw before. It's just we're explicitly stating here that, well, the second parameter of our function, filter movies, is going to be a pointer to a specific flavor of functions, one that returns a Boolean and takes in a single parameter, or has a single parameter of type movie that is passed by reference to const. So invoking this is pretty much identical to what we've seen before. We can go ahead and initialize results with the filtered collection of movies that are filtered according to, well, this criteria, released before 1990. So we go ahead and, again, we're just similar to how we'd pass an array to a function. We're just writing the name of the function, and it's going to be used to initialize this parameter. Whoops. This parameter. So the address, you can think, to the function released before is used to initialize the filter function. And then when we call filter with the call operator and pass it a movie collection, well, this function in that case is going to be invoked, and movie is going to be used to initialize the parameter movie. So function pointers, some advantages and disadvantages. So advantages is there's minimal syntactic overhead, and we'll contrast that with function objects, which are coming up. One disadvantage is that they do not retain state within a scope, and you'll kind of see the implications of this again when contrasted with function objects. So with that, all of that in mind, let's go ahead and move on to function objects, and then we'll close out today's lesson with defining higher order functions that accept function pointers and function objects.